For part A of this problem, a free body diagram, we have to look at our two masses here, 8 kilograms and 4 kilograms, and decide what kind of forces are acting on them. So let's look at the hanging mass first, the 4 kilograms. 4 kilograms, we got force of gravity, because it's just hanging down, always force of gravity there, and it is connected to a rope. Tension in the rope acts upwards. Now similarly, for the 8 kilogram mass, there's force of gravity acting down. There's also tension in the rope, but now the rope is on the right side of the 8 kilogram mass, so it's to the right. There's a normal force up because it's on a surface. Normal is always perpendicular to the surface. And the other side of the 8 kilogram mass, there's a spring, so there's a spring force holding it back. Now for part B, calculate the tension in the string. If we look at the free body diagrams above, we see that both masses have an FT in it. So how do we know which one to use? Well, if we use the 8 kilogram mass, we don't know what the spring force is yet, at least. So we can't really use the 8 kilogram mass to figure out what the counteraction, so to speak, there is in the tension in the string. But we do know that the 4 kilogram mass, force of gravity down, FT is up. Now, the 4 kilogram mass is not moving. If it's not moving, it's not accelerating, so therefore the force of gravity has to equal the tension in the string, and we can always find the force of gravity as long as we know we're on Earth, and of course we know the mass. So the tension is 39.2 newtons. For part C, similar to part B, we want to calculate the spring constant of the spring. Now, we have to look at the 8 kilogram mass because that's the only one with a spring force. That's what it's connected to. So we look at that free body diagram from part A, and we see that Ft is in the opposite direction of Fs. Now, just like the 4 kilogram mass, the system is in equilibrium, so it's not moving, it's just kind of sitting there. So similarly, that means that the tension in the rope has to equal the spring force. Now, we already know the tension from part B. It's the same rope as it is for the 4 kilogram mass. So tension is the same. And we know Hooke's law. Hooke's law is Fs is equal to Kx. And X, now we got to be careful. X is the stretch or compression of the spring. In the problem, it tells us that it has an unstretched length of 0.2 meters. And then at the very bottom of that paragraph, it says the length of the spring is 0.25 meters. So we want to look at that difference. Think of it like a displacement. The difference is 0.05 meters. So we use that for X, and we get a K value of 784 newtons per meter. Now for or part D here, there's actually a typo in this problem. So the way I solved for this initially, I basically solved for the problem as if the spring was cut. So I kind of set it up as if the 4 kilogram mass and the 8 kilogram mass were both accelerating together with the rope. But that's not the case, so we're going to kind of ignore the work here, but I'm just going to talk over it because it's very similar. The string is cut at point P, which we can see is to the right of the 8 kilogram mass. So the 8 kilogram mass isn't going to go off the table, only the 4 kilogram mass is going to fall. Now it's a massless string, so really since we only care about the 4 kilogram mass falling, we know it's going to accelerate at 9.8 meters per second squared. So you can ignore the left side of part D, all the work that I did there, because again we know the acceleration is just negative 9.8. And we use the kinematics equations to figure out how long it takes to fall to the ground. Now everything else remains the same. The only difference is instead of 3.27 for acceleration, we use negative 9.8. And technically the displacement should be negative 0.7 since it falls down. So same equation, you do the math, and you actually get an answer of about 0.38 seconds. Now for part E, to calculate the maximum speed attained by the 8 kilogram block as it oscillates, okay, well again, now the string is cut, so the 4 kilogram mass and rope is gone, and we know that the spring was stretched out 0.05 meters, or 5 centimeters. So that being said, when the spring is stretched out, when we're talking about speed here, trying to find speed, we know that this is a conservation of energy problem, because there was potential in the spring when it stretched out, and as the mass starts to slide, as the spring wants to go back towards equilibrium, it has to get converted into kinetic energy. So at maximum speed is attained at equilibrium at that 20 centimeter mark. So we know that the potential in the spring, 1/2 kx squared, has to equal the kinetic energy of the block since they are attached together. So we set it up as you can see here, and we see that the maximum speed, the velocity at that particular point at equilibrium, is 0.49 meters per second. Now, one thing to point out, as it keeps sliding even more to the left past this point of equilibrium now, it's going to start to slow down. And one thing to note about part E here in this case, in general, is that the force, when we talk about springs, force is not constant. The acceleration actually changes. This is really the only time we see that in any problems is when we deal with springs, because the force depends on the stretch. The less stretch there is, the less force there is. So it's actually not a constant acceleration like we usually deal with.